Okay, this is IM1, this is 5-3. Hopefully you watched the first video where I compared linear and exponential functions, but just to reiterate, a linear function is going to be written as y equals mx plus b, or one of the other ways that we can write it, but the x is going to be in line with everything. This is linear. We're not raising anything to any power. Exponential is going to have some number, let's call it n as any number, with x as the little number. So the variable is the little number up here. When we look at them as a table, these are going to be adding the dependent, and these are going to be multiplying. All right, so let's go down to problem 1. So problem 1 says, does the table or rule represent a linear or exponential function? Well, let's find out. We went from 1 to 2, and we went from -1 to +1, that's +2. We went from 1 to 3, that's +2. Went from 3 to 5, that's +2, so this is linear. Let's look at B. We have x as a variable, x as an exponent, So we know that this must be exponential. I'm going to turn the page. Okay, I turned the page. I'm looking at problem 2 now on page 302. So it says, can you model with a linear function or an exponential function? All right, Jack pays $30 each month for gym membership. So we could do that, and we can even make a table if we wanted. So on the first month, he paid $30. On the second month, he paid $60. On the third month, he will have paid $90. On the fourth month, he will have paid $120. And what we see is we're adding $30 to each one of these. So this is linear. A culture starts with 1,200 bacteria. The number of bacteria in the culture is halved each day. All right, so we start on day 1, we have 1,200. On day 2, we have 600. On day 3, we have 300. On day 4, we have 150. And what we see very quickly is we're not subtracting here. We're dividing by 2, or we're multiplying by a half. Times a half, times a half, right? So this one must be exponential. I'm going to pause for a second, and I'm going to turn to problem 3. Okay, in problem 3, we're looking at rate of change. Rate of change is found by the second dependent variable minus the first dependent variable over the independent variable minus the independent variable. We sometimes write this as y2 minus y1 over x2 minus x1, which should look super familiar because this is also slope. All right, so when we ask, the question is, if we went back and looked at Jack and his gym membership, for the first month he paid 30, for the second month he paid 60, for the third month he paid 90, and for the fourth month he paid 120. What we can see is each time the rate of change. So if we did a rate of change, we would have 60 minus 30 over 2 minus 1. So that would be 30 over 1, which equals 30, right? But if we came down here to the bottom one, we'd have 120 minus 90 over 4 minus 3. This would also be 30 over 1, which equals 30. So for a linear, the rate of change is constant. If we did the same thing and we looked at that bacteria culture, or if we look at question 4 where something doubles every day, I'm just going to quickly say something doubles daily. On day 1, let's say there are 2. On day 2, there are 4. On day 3, there are 8. On day 4, there are 16. On day 5, there are 32. So what we see is the rate of change here, 4 minus 2 over 2 minus 1 equals 2 over 1. But the rate of change here, 16 minus 8 over 4 minus 3, that's 8 over 1. So the rate of change is not constant. For exponential. Question B asks us if they will eventually overtake. Hopefully you guys have been looking at about 1,000,000 graphs, right? But if not, if we have a constant rate, that's a linear graph, what we see is that this one might start off slow, but as you've seen in all the pandemic graphs, sooner or later, it's going to overtake it, right? This doesn't have a constant rate of change, but it's going to start to get faster and faster and faster.